In this presentation, we'll cover the use of magnetic fields in cyclotrons. So you can pause the video here and have a look at the learning outcomes and revisit it after the presentation to check off that you understand the concepts. I'll just do a quick introduction and a bit of background on cyclotrons. So in nuclear physics and medicine, sometimes necessary to accelerate charged particles to high speeds and high energies. So these are used to form isotopes of other elements, and they can also be used to study. So one example is when you fire deuterons and accelerate them to high speed into uranium, you can actually make plutonium out of it. When we want to accelerate a charged particle, we can use an electric field to accelerate it. Now, when we're looking at some particles and in making isotopes, these particles need to get to very high levels of energy and very high speeds. Now, it is difficult to create a potential difference of the required magnitude that we need due to the high energy requirements and the practicalities of it. However, what we can do is to get to the order of magnitude that we need, which might be giga-electron volts, for example, we can pass the charged particle through smaller incremental potential differences, and these smaller steps actually get us to where we need to be. So I've created this graph here that helps explain this. So on the y-axis on the left, we've got a velocity, and it's unitless, it's just used as an example, and we've got a time interval on the bottom as well. So we've got a particle that's traveling between the D's and within the D's. So between the D's it's actually accelerating due to the electric field, and within the D's it's just changing direction, however maintaining its speed. So we can see these flat components where the velocity is not changing on our graph. So I've just marked one here, and it's the arrow is pointing to it. The velocity remains constant, and it is within the D's because the direction is changing. When we have a sloping portion of the graph, such as this bit here, the particle is between the D's or in the separation space, so it's within the electric field, and this is where the velocity changes and increases. So instead of having extremely high potential difference from here to here, we can do it step by step, and that's why the particle is in the circular path, and it incrementally accelerates. When a particle is traveling within the D's of a cyclotron, there is no electric field, and the particle is only subject to the magnetic field. Now, the particle is actually traveling at right angles to the magnetic field, as for example in the diagram, the magnetic field is traveling into the page, and the particle is traveling in the plane of the page. So it's traveling at right angles to the field, and we can use our right hand rule to work out the direction of the force. And in this case, our particle starts at the bottom, a positive charge, and we can use our right hand rule and find that the force is up in the first instance at point P, and as we go around, the force is perpendicular to the particle and changing due to the direction. The motion of the particle within the cyclotron is a spiral path, as we previously covered, and the radius of the path can be given by the formula R equals mv over qb. So when we have a potential difference that is applied to the D's, the electric field is in one direction between the D's in that separation space. But we know that a particle, when it travels in a cyclotron, when we're looking at our diagram, it goes left at the top, for example, and right down the bottom. So it actually changes direction. So what we need to do is we need to change the direction of the electric field so it synchronizes with the movement of the particle. Now, to do that, we need to know the period of the particle as it travels in this cyclotron. So we want to work out the period of travel for the particle in the cyclotron. So what we can do is recognize that to work out the time, the period, is actually the distance divided by its velocity. So that is what I've got here. Now, the distance is the length of the cyclotron, or the circumference. So that's given by 2 pi r, and we can substitute that into this equation, but now we can find a better substitute for velocity. We know that the particle's radius is given by this equation here, which we introduced previously in another slide, and we can rearrange it for velocity. Now what we can do, we can put this equation, which I've labelled 2, and we can substitute it into 1, and we end up with our result that the period is equal to 2 pi m over qb. So just looking at our equation that we've just derived, we can see the time to complete one revolution, which is the period t, is actually independent of the velocity of the particle. So all that the period is based upon is the mass of the particle, the charge, and the magnetic field. Now, knowing these quantities, we can work out the frequency that we need our alternating potential difference at, and the frequency is the inverse of the period. So this is given at the bottom of this page, and the frequency is equal to the charge times the magnetic field strength divided by 2 pi times the mass. Now we're going to look at another derivation. So each time the particle crosses the separation space between the Ds, now this is where the electric field is, it accelerates and gains kinetic energy. So this is given by the equation of delta K equals Q delta V, where Q is the charge of the particle and V is the potential difference across the Ds. Now, if we know the size of the apparatus, or the maximum radius that the particle can take in the cyclotron, we can find the total kinetic energy as it leaves the cyclotron. So we can use our equation of K equals half mv squared, and we can replace this V. When we look at our radius equation, when the particle is moving, we can rearrange this equation for V, and this is what we get inside the brackets. And we can derive our formula for kinetic energy when the particle leaves the cyclotron, which is given here.